Greetings, let's get started again. Let me go back to the textbook and see what we got going. So here's our textbook, and let's, so 1.3. So yeah, we talked about square roots, and earlier we mentioned how it very much matters if the plus or minus sign is not inside the radical. And like here, we add first because the plus sign is inside the radical in part C. And we'd add the 25 and 144, get 169 because there's parentheses around the whole thing inside part C. And we'd get square root of 169, which is 13. Whereas in part D, the minus sign is outside. So we do the radicals first. We'd do radical 49 is 7, radical 81 is 9, 7 minus 9 is -2. Now, when I closed off last video, remember I warned y'all, you can only do this for the product of two positives. The product, this is great, right? Radical AB is radical A times radical B. This is great right here, right? You can do this. This is in y'all's book, which y'all have access to. But remember, I warned y'all, you can't do this for plus or the analogous for minus, and you can't do this for subtracting either. For adding and subtracting, you can't do radical. For example, for adding, you can't do the square root of entity A plus B is the square root A plus entity square root B. It won't work. Now, for multiplying positives, it's great. Anyway, that see the last video for that. Now for square roots, you can filter out like the square root of 300. You can filter. You want to bust 300 down to the biggest perfect square that will cut into it. Bust 300 down to the biggest perfect square that will cut into 300. That perfect square is 100. So we have 100 times 3. Now here's the thing, you can bust that up as radical 100 times radical 3. The square root of 100 is 10, so it's 10 times radical 3. Now if you have something more convoluted like part B, you can do, 162 is kind of wild. And anytime you get an odd power, you want to make it even. So you take 2 out of 162, make it 81. 81 times 2 is 162. And you take a out of a to the 5th right here, make it a to the 4th right here. Now b to the 4th we're happy with, so we get that. Now here's what happens. You divide all the exponents by 2, so when you take it out, now the square root of 81 is 9, right? Now, so the square root of a to the 4th, you divide by 2, that's a squared. The square root of b to the 4th is b to the 2, b squared in other words, times, now the square root of 2a can't really change. It just is what it is. So we have it right here. So there's the final answer. 9a squared b squared times radical 2a. And I'll leave it to you to bear this one out. Now this one, some things are better left brought together. We can bring the 12 and 3 together as 36 in example 3 here. But the square root of 36 is 6. And in the trit problem, the square root of 100x squared is 10x, assuming x is positive, right? So this would be 10x here. Now what works for multiplication is good for dividing. Dividing is also pretty friendly. Now we're assuming positives, right? Negatives kind of mess things up for both dividing and multiplying. But we're assuming positives, and we're assuming that b is not 0. We don't want to divide by 0. But anyway, the square root of a over b is radical a over radical b. Adding and dividing Let's go back up. Multiplying and dividing are nice. Adding and subtracting are not nice with radicals in a certain sense. So that's the algorithm right there. Example 4, you can break this up. Radical 5 over radical 36, but that's radical 5 over 6. Remember, we don't like radicals in the bottom. And try this one. now, see if you get x over 3y squared times radical 2, where radical 2 is in the numerator. Okay. You could also put x times radical 2 over 3y squared. That may be more elegant. X radical 2 all over 3y squared. For this one. Now, example 5, remember with a square root, we don't like odd powers. So, you actually here, let's forget that. Let's just bring it all together. Forget the whole thing. The y's cancel. Now, remember by the laws that we went over, the exponent laws, 11 minus 7 is 4. So we have the square root of 9x to the 4th, but square root of 9 is 3. Divide by 2. When you do the square root, you divide the exponent by 2. So it's x to the 2 power. The exponent that we ended up with is 2. For the triad problem, bear it out and see what you get. Not much comes out of the radical. Now, let's see. What stays in the radical? Your final answer is going to have a radical in it. B to the 4th comes out, right? Now, what stays in? You'll get b to the 4th times radical 3ab. B to the 4th on the outside times radical 3ab. That's what I'm getting. Check it and see. You do this right here, but anyway. Now, careful with adding and subtracting square roots. I said it was not nice, but there are things we can do. It's not as good in a certain way, but there are things we can do. Like if you add two radical, some things just don't gel, and that's all there is to it. But some things will gel. Like if you have radical 2 plus radical 18. Now, radical 2 is understood to have a 1 in front of it, so it's 1 radical 2. And radical 18, remember, that 9 times 2 is 18, so 9 comes out as a 3 right here. Remember, you can do that so we have 1 radical 2 plus 3 radical 2. The 9 comes out. But hey, these are like terms. 1 times x plus 3 times x is 4x. But this time we know who x is. In this special case, x is radical 2. So it's 4 radical 2. 1x plus 3x is 4x. 1 radical 2 plus 3 radical 2 is 4 radical 2. Now, we got very lucky. Most of the time, radical 5 plus radical 7 is just a sticky, irrational number that won't gel, right? It's an irrational number that won't gel. Now, 4 radical 2 is irrational, but it did gel. Now, how to? So we simplify each radical expression with the radical 18, or each one that we can. The radical 2 didn't really simplify. And we add accordingly. The 1 and the 3 made the 4. So example 6. Now, we can't just do it right away. Radical 12, 12 is 4 times 3, right? So now you can do two things. That 4 can immediately jump out as a 2, or you can bust it up like they do right here. So it's 5 times 2 times radical 3. So we get 5 times 2 times radical 3. That's kind of the long way to do it. That's 10 radical 3. So this first one here is 10 radical 3. Now the second one, the plus sign 2 radical 3, 2 radical 3 won't really do anything else. So we have 10 radical 3 plus 2 radical 3. That's 12. Do that right here where my cursor is. Hey, these are like terms. That's 10x plus 2x. That's 12x. 10 radical 3 plus 2 radical 3 is 12 radical 3. So addition and subtraction do give in a little. You can subtract in the analogous manner that we're adding. Like 10 radical 3 minus 2 radical 3 would have been 8 radical 3 if we'd have done it that way. If we'd have subtracted instead of added. But anyway, like here, in this one right here, 4 times 5, so 4 comes out as a 2, right? Square root of 4 is 2. 6 times 2 is 12. So 1 radical 5 plus 12 radical 5 is 13 radical 5 for this one. Now let's look at example 7. You take out all you can take out, but you got to be careful. we're not assuming everybody's positive, and that's going to create convolutedness. Well, we got to be careful. Yeah, A would have to be positive. Well, does A have to be positive? Does it? If A is negative, we're in trouble anyway. I say we don't really need the square root with A, because if A is negative, we're toast anyway. We're taking the square root of a negative, cube of a negative is negative, and would be imaginary, would be toast. So really, this square root here is in vain anyway. How does it go if you, anyway, if we don't assume A is positive, we're in trouble, right? So this is kind of badly done. But anyway, they just go ahead, and if you have, from algebra 2, if you have the square root of an even power and you get an odd power in return, that's when you need the absolute value. If you take the square root of x to the 6th and you get x cubed out, you do need absolute value. But here we don't really need it. That was actually silly. That's just A. And B would have been in danger. If anybody would have been in danger of needing absolute value, it would have been B. But we got B squared, so we don't need it then either. And C is to the 1 power, so we're dead meat anyway if it's negative. So it doesn't. Nobody needs absolute value. But anyway, you take out what you can take out. You chunk the radical. 72 is 36 times 2. Just do 36 times 2. Square root of 36 is 6. 6 times 20 is 120 here. So you get 120 AB squared. Remember, divide by, now A cubed, you want to do A squared times A, and that A squared comes out as an A. Right, like that. And again, if A is negative, we're in trouble here anyway, right? So A would have to be positive from the get. Or 0 maybe, but it had to be non-negative from the get. Now, so do, A squared times A. And for B to the 4th, we're happy, it's even. So do half of 4 is 2, so B squared. C can't come out, C's not coming. Now for 72, we had 36 times 2, but the 2 can't come out. So we got 20 times 6 times A times B squared times radical. We had that 2, that A, and that C that didn't come out. So we got 120 AB squared times radical. Now, that 20 was already inherited here, right? So we had to contend with it. That 6 multiplicatively bumped into it. And you could do it their way, right? What they did was they just chunked 72 into 9 times 4 times 2. You could chunk it into radicals like this, and that's fine. It's all the same. Radical 9 is 3, radical 4 is 2, right here. And now the radical 2 times radical A times radical C here, they just reconsolidated them. Anyway, I found that to be sloppy, but it's correct. But they don't need the absolute value bar. Now this one down here, do it the analogous way. That 14 is inherited. The only thing that really comes out, we can chunk it up. That radical 4 is a straight up 2. 2 times 14 is 28. You'll get the same like term. You'll get 120 x, cough, cough. You'll get 28x, cough, cough. And now we're subtracting them, right? 120 minus 28 is 92 here, right? So we get 92 times this ugly term here, right? So we get 92, just regular A, okay, times B squared times square root of entity 2AC. And I'll leave this one for y'all to do. You'll have to do some cleanup. And I'm out of time on the video. Thanks. See y'all in the next video.